Okay, this long-term evolution, it kind of goes backwards in times, forwards in times, and also goes into exoplanets. So there's a number of different topics that we're going to touch on and talk about. So, and at this time, the word geospace is a little bit more than just the ionosphere, but let's kind of begin. Okay, so that being geospace today has all kinds of technologies with which we measure all kinds of good stuff to do with space weather and geospace. So the question to you is, how the heck did we know geospace existed a long time ago? It's post-lunchtime, and I know you want to relax, but you're not. Yes, ma'am? Compasses, oh, okay, that's the magnetic field. That does actually come in, but we actually did things before that. So you're right about the compass, yes. Lightning. Well, I'm not going to call that space weather. No, we're not going to do lightning, no. Seeing auroras. Okay. No, that wasn't a trick question. That was a brilliant question.
When I was a lad, a tiny wee lad, my mother said to me, "Come see the northern lights, my boy, they're bright as they can be." She called them the heavenly dancers, merry dancers in the sky. I'll never forget that wonderful sight, they made the heavens bright. The northern lights of old Aberdeen mean home.
We can let this go a little.
The northern lights of Aberdeen are what I long to see. I've been a wanderer all of my life.
Okay, so this then is the Aurora. Now this is called a quark, way to the north of us if we're in the northern hemisphere. This is kind of how it looks. Notice a rainbow in comparison is a pathetically regular thing. This is dynamic and wanders across the sky. And one looks up at that, and then one looks at what modelers do. We kind of integrate over 100 kilometers horizontally. So this is always amazes me that our models even work when we put Aurora in. This is a really special thing. If you're underneath the field line and you're looking up where the arc is right above you, it's called a corona. It's going off in all directions, and your head can't move enough directions simultaneously to see this. So you need an all-sky camera type of thing. So the corona is this other form. But what you see is, in the Aurora, almost always, there's structures on all kinds of scales. So when we talk about the Aurora dumping energy in, it's dynamically dumping on time scales of fractions of a second to minutes to hours. But then the spatial scale over which it's bright is kind of very variable too. So these two things do generate mankind's first real impressions of there's something else out there, and I'd call that geospace. So here's a little exercise. Many of you are from countries in which, well, the Aurora doesn't occur often, but the Aurora has different names and different, in Scotland they were referred to as the heavenly dancers, which were quite polite and nice. That wasn't the case all over the world. So I think Nick would receive from you, you can post if you have an enthusiasm from your country, what the Aurora was called in your language, an English translation, plus the name of the country. And we'll see if there's any takers to generate some. I thought I was doing well just to use the word post. Yeah, But Nick, yeah, however you work with Nick to get him information, please do that. Okay, so that's just a connection between us as humans and geospace. This is perhaps more along the lines of what you might be expecting when we talk about history. It is believed, but there's no real proof. These cave structures, referred to as macaronis, could be Aurora, and therefore would be one of the earliest evidences that mankind noticed the Aurora and treated it as something special. Most certainly, by the time we get into this era, a few hundred years BC and then the early years thereafter, the idea of writing and describing Aurora. Now, it's, of course, very subjective. The vocabulary that they used did not use the word Aurora, which was not, of course, defined as we know it today. It's a very subjective analysis. But the one that's perhaps not so subjective is the sunspots, the presence of these on the disk. So between Aurora and sunspots, we've got, 2,000 years ago, very clear evidence that people were concerned and I suspect made bad decisions based on such sightings rather than good decisions. Okay, and then we get more scientific. And 1600s, there were in various places scientists who were starting to collect data on sunspots. And then, unfortunately for them, they went away. Not that the humans went away, but the sunspots went away. What was this period called? Maunder minimum. Okay, so for a good part of a century, they went away. They went away in the visible sense. There are strong arguments today as to what level of solar activity was present, and it wasn't zero. Then William Herschel. This is perhaps where a connectivity between space weather, or maybe just space climate, if you like, and what affects us down on the ground. There were really bad harvests. The Thames froze over. There's a few other things associated with this time period, but this was where people were starting to think maybe there was a connectivity. And as the student said earlier on, magnetometers started to detect things. I think the Carrington event in 1859 is the premier event. Not only was it perhaps the biggest event in recorded time that hit the Earth through its aurora being seen almost down through the Caribbean towards the equator, but at that time, a magnetometer making measurements in London at the same time as Carrington was doing the sunspot observations and detected the flare. A few days later, they connected the magnetic variation with the visible aurora, and that perhaps was the first connection between what we now call space weather, the ionosphere, magnetosphere, CMEs and flares and other things all active, and there was a connection. And of course now everything's going to move forward. The number of ways in which we can detect geospace, monitor geospace, is fairly enormous. From the ionospheric point of view, the big breakthrough was the use of GPS. The problem we'd had prior to that was single point type measurements, whereas GPS got around that in a very big way. We got thousands, if not hundreds of thousands of observations at any instant in time. So that's the kind of step forward that we've gone through. Okay, so a working definition of what we might call geospace. We could argue the outer boundary is the magnetopause bow shock, and the inner boundary is the lower ionosphere. This part we call the SARE. Between these two, we've encapsulated a volume, if you like, around the Earth that we could call geospace. The outer boundary interfaces to the solar wind, while the inner boundary interfaces to the atmosphere. Okay, I'm now going to go into a model. There's 3 models that have been created that were capable of looking at what might happen during Maunder minimum and a Maunder maximum kind of condition. What would the ionosphere and thermosphere do? So the main thing, the takeaway here is that the solar irradiance is 1340 watts per meter squared. And when we talk about the ionosphere and the EUV, it's pathetic. It's 2 or 3 milliwatts per meter squared. So that is creating all of this stuff that we're here talking about, the geospace environment. These are the sources of the ions. Solar maximum, it's about double. You might say 2.5 times milliwatts per meter. So a Maunder condition would be these kind of irradiances, half this value or less. A Maunder maximum would be doubling or tripling this value. And that was the objective of these scientists. Professor Roble, who was at NCAR here until he retired. Myself, I had a graduate student, Chris Smithrow, built a model, and Tian here at the university built another model. So these models were designed to try to see what happens when you dump in heat beyond solar maximum. How stable is the atmosphere? What are the changes? So let's do Maunder minimum first. Okay. Okay. One could argue. Okay. So EUV determines geospace climate. It's a stretch. There's many people who would disagree with me. Okay. So this is the first thing. EMSIS, we kind of showed it. Looked at the second view graph this morning, where we showed how solar minimum, solar maximum, winter, summer variations generated the different atmospheres. We're looking at O, N2, O2. This upper panel is for minimum, solar minimum, and this is solar maximum. So this is just a reference, and this is just to prove that these special models, they're one-dimensional, they're only altitude, they're integrated global models. So they're not useful if you're trying to look at particular phenomena or structures, but to look at an overall response. They're not unreasonable. The fact that the two lie on top of each other is what you might call our calibration across a normal solar cycle. So we've ground truthed them. The upper atmosphere present day climatology. So what is the name of this atmospheric layer? So this layer from 150 upwards is the one that is influenced significantly by Maunder minimum, Maunder maximum. What's the word or the name we give to this layer in the neutral atmosphere? Thermosphere, that's it. And the word thermosphere has a connotation automatically about temperature and energy. Okay, so now moving forward, this is then these two models being run, this time to look at solar minimum, solar maximum, the ionization states. So the minimum, O plus is dominant, and then we end up with our molecular ions generating the kind of lower altitude E region. And again, solar maximum, O plus is significantly enhanced, but the E region is a little enhanced, but not by the same factor. Oh, for that one student who likes N plus, where are you? Sorry, can you? Oh, there you are, sorry. There you are. The model generates N plus, and it's significantly lower down, right? We had a conversation, right? Okay, so N plus, and this is what the energy looks like. Again, under solar minimum conditions, like we talked before, there is this lower, below what we would then call 120, our SARE region. It's constant. But the neutral temperature, the exospheric temperature, and the ion temperature are similar. But TE, with all these photoelectrons and all of their energy, the electron gas is quite a bit hotter. This was the minimum, and this is maximum. And the maximum has some more interesting structure. But again, the altitude scales are changing too. So as we put heat in, the scale heights change, and we have to look at different altitude scales. Although, from a pressure point of view, the pressure scales are the same. But their equivalence in altitude has changed because we changed the scale height and the density distributions. Okay, so why are the day-side electron temperatures elevated? Sorry, I've just told you that, right? Okay, the electrons are coupled to a hot magnetosphere reservoir on the top side that has a weak solar cycle dependence. Okay, this is just to remind you that if you're at the equator, you're not coupled to the magnetosphere. But if you're at the polar regions, Okay, then your upper boundary condition, whatever it is, either goes into the plasma sheet or the lobes, and they're coupled to an electron gas of different temperatures. And our upper boundary condition up here can then be driven by what the magnetosphere is doing. But in our case, we just have a very no thermal flow. Okay. So now if I want to do Maunder minimum and Maunder maximum, I have to have a new solar spectrum. And that's what this figure is going to talk about. The horizontal axis is our energy flux. Remember how pathetic it was? It's milliwatts per meter squared, the irradiance, in the EUV. This is the main driver. So S equals nothing, S equals 1. So this set of units was created by Chris Smithrow. 0 refers to our present-day solar minimum, and the energy flux is at 1 as 2 to 3, but the exospheric temperature is about 600 Kelvin. Our solar maximum sits up here at 7 to 8, and we call that S equals 1. And the various measurements and models of this energy flux in the EUV tend to find it's linearly correlated with solar activity. So as the energy flux increases, it's not a surprise perhaps that the exospheric temperature is increasing linearly. So on that basis, we pushed Maunder minimum in the negative direction. So we could extrapolate this down. You can't extrapolate far before the energy flux goes to 0. But of course, remember, there is still an atmosphere beneath you which sustains a temperature. So there is an end point here. It's not that we're going to run negative temperatures. The model won't go down here. Okay, so the grand maximum, which is one of these events which we believe occurred 1,000 years ago or more, the multiplying factors range from 2 to 3, and the temperature would be expected to increase on this side. And the question is, what's going to happen to our atmosphere and ionosphere? As a consequence of that, would we care? Okay, so the Maunder minimum, we're going to drop to, on that S scale, minus 0.5 to minus 1. And then we're going to ask what would happen. Would we even know geospace was affected? And hint, for 100 years, humans have developed technologies that depend on geospace. So let's see what would happen. Here's our ionosphere at S equals 0, which is Maunder minimum, is a normal minimum, solar minimum in this panel. And as we go down, we get more negative, i.e. the EUV fluxes are decreasing. It's a logarithmic density scale, so you're looking at densities. And as you kind of turn off the EUV, as expected, the O+, and in which case the total electron content is going down. A number of other things are diminishing or decreasing. The height of this layer, the nomenclature HMF2, refers to the height of the F2 peak, which is the dominant O+ peak. The NMF2 nomenclature refers to the density. So these are our normal solar minimum values. And you can see that the layer is decreasing as things get colder. And the density as well is decreasing. Okay. Yes, sir. It's all, okay, so the word quasi-neutral. The electron density is always in this kind of transport formulation equal to the sum of the ions. Although I did point out that the minor ions, we don't bother with them. We don't add their electrons in. So there's some slight inconsistencies. Okay, so here's the takeaway message. Under Maunder minimum, radio waves used today to carry over the horizon radar work will not go over the horizon. The critical frequencies of our ionosphere have dropped so much that our normal 10 megahertz OTH work won't work. But satellite drag would be insignificant in today's LEO orbits. So all the satellites sitting up at 200 or 300, 400 wouldn't even realize there's any atmosphere left there. It would be a great place for them. The geolocation, so here's your GPS, would be almost independent of the ionosphere. the corrections for the order of magnitude reduced electron density total content would go away. Marconi's transatlantic first radio communication might not have worked, and we would not have an ionospheric physics community. Okay, so that's our modern minimum. So let's go to the other extreme. This one has more relevance perhaps to exoplanets, but let's start. There was a grand maximum somewhere around 1250. Now our database on what all happened is somewhat limited, but scientists, solar scientists, have tried to recreate reasonable EUV curves. Basically, our S index will do that for us between 2 and 3, which means that the EUV integrated irradiance would be between 14 and 21 milliwatts per meter. So this still has not affected the solar constant. The expectation that this change has any impact on the atmosphere in general is nil. It's not really going to do much. The Tian model in particular was able to go to even higher values. Our one just about stretched up to 2 and 3 times. So there's a couple other models out there today that can do this. Here's the takeaway message. Okay, what you're looking at is our horizontal axis is the solar EUV, integrated flux in milliwatts per meter squared. So our solar minimums here and solar maximums here. And these 3 points are then repeated just for reference. And then beyond that is what we call the solar, the grand maximum. Okay, I won't talk about this. This is another index rather than this index, and they're assumed to be linear. But over here, the exospheric temperature is the first thing. So as we start putting in more EUV energy, the models, particularly the TN one and our own one, do show this almost linear increase in exospheric temperature. Now, 3,000 isn't a problem yet. But as we'll talk about later, if we get up to 5,000 Kelvin, we start getting blow-off conditions, Jane's escape, and then our atoms, 5,000 would pertain to hydrogen. It would just blow off. We couldn't hold it. Gravity wouldn't hold it. If we get up to about 8,000 or 9,000 Kelvin, this is nowhere near, then something like helium, oxygen, atomic oxygen would just blow away and we'd be in real danger. But for this range that we are looking at, there's nothing too detrimental here yet. The total electron content, so now your GPS is not so happy. It's just linearly ramping up and almost faster than anything else. So TEC is increasing. Over here, from the point of view of the number density at the peak, if you like, of O plus, the F layer peak, the other species that we've been talking about, they saturate. The chemistry for them saturates. The temperatures got so large that the rate at which you're recombining is keeping up with the increasing rate of production. So in actual fact, they level off, with the exception of N+. N+ is sitting down here in its kind of minuscule form and gradually ramping up. So it's becoming a more interesting ion. But this is for conditions that we've never experienced, or maybe 1,000 years ago they experienced them. Okay, so for the extreme maximum, okay, the layer height changes as well, from 360 kilometers up to 500 kilometers. This has some real impact on what we call LEO, the low Earth orbit. If the neutral gas is kind of bolstered up through a scale height change, our normal LEO is not a very good place for satellite drag place, so we'd have to move everything higher. The O plus peak saturated. However, TEC, now the saturation of this peak didn't mean that the total electron density saturated. It's just that the peak became a very broad peak, and the TEC was increasing linearly. The kind of values we were talking about meant that present-day GPS would work, but the errors would most certainly start moving well into the tens of meters unless one used 3 frequencies or the more sophisticated GPSs. Okay, exospheric temperature was also increasing. But although we got up to 3,000, this isn't troublesome for us. We'll talk about what trouble would look like later. Okay, so do we need a break? I know you've just got over the lunch and you're still enthusiastic. I haven't seen anybody drop off yet, so we're kind of still good. We can have a short break, but otherwise I'll just continue. Who wants to continue? Okay. I asked that way. I mean, if I asked the other way, who wants a break? Oh, wow, that's country. Dana, you didn't answer. We'll just continue. Yeah, that's good. Okay, so what we're going to do now is talk about space weather impact on the geospace climate. There are 3 things we've touched upon, so you've already got some ideas where we're headed with this. There are 3 main aspects of how energy is going to get into the upper atmosphere, change the atmosphere, change the ionosphere, and hence introduce what you call a direct correlation to space weather. So the first one is the Aurora, and we've talked about that, under geomagnetic storms. The X-class solar flares. Class is smaller than X, and that's an order of magnitude less irradiance, aren't too interesting. But X-class, especially the large X-class, do damage. Joule heating associated with large magnetospheric cross-tail potentials. And this one and this one, 1 and 2 are kind of interesting to study if we go to exoplanets. There is an indication that the magnetospheres may actually saturate the electric field. In our system, for big storms, there is an indication that the cross-tail potential, this big electric field, tends to saturate below 200 kilovolts. Okay? If that's true, then the magnetosphere or magnetopause is a regulator, and you don't get, the solar wind is more intense, the CMEs are more intense. There is an internal mechanism that's preventing this just dumping more energy into the atmosphere. So when we talk about projections, it's pretty hard to project since we've never seen a magnetosphere for an exoplanet, nor have we seen CMEs on stars other than our own. So there are these 2 things that are kind of out there as major question marks. This one isn't a question mark, as you've heard about, but we'll talk about. Okay, so the context under which we're going to do this is as follows. It's thermal energy density. So if I take just our solar medium neutral atmosphere in some global average, we've got species. There's N2, O2, N2, O2, and O as the dominant ones. They all have a particular temperature, so that you can do a simple calculation of the thermal energy density. How much energy in the kinetic sense is there associated with it? And you get a curve like this. This is altitude. Here's our 100, 120 region again. And the blue line is the sum of all that energy. It's on a logarithmic scale, and it's joules per meter cubed. So that's our thermal energy. And what I want to do is, if we take a very strong aurora, or a very strong X-class flare, or a very strong Joule heating event, and integrate over a reasonable length of time, how much energy are we putting locally into the upper atmosphere? If the energy density exceeds this in a time short compared to the relaxation time for the atmosphere, you know that it's going to be turbulent, very messy, and it's going to change things. If it ends up over here as only a fraction of percent, then the flare, the whatever, has no effect on our atmosphere and hence geospace. So I'm treating this as the ionosphere through the Sayre boundary is a source for geospace. It gives its particles, its neutral species. The radiation belts get energized, atoms that come from the ionosphere. So in some way, this is, if you can change this, then you're going to change geospace. So combine the neutral density and temperature information produces an altitude distribution of what I call the thermal energy density. There's other energies in the bonding and the excited states if they become particularly active. For molecules, you've got rotational bands, you've got vibrational bands. So there is other energy, but this is just a layman's approach, okay? So that's the question we want to kind of ask. The hydrostatic is if the time constants aren't kind of, or other things are happening on longer times, then we stay in hydrostatic. It could be a little bit bumpy, if you like, but not going to change things markedly. Okay, so here's our first input. The Aurora, which a lot of you have not seen, is in general a region around the poles, but not in the polar region. So in the middle, there's an empty space, and I used that very carefully. There is Aurora in there under certain conditions, but the bulk of the emission is in what is a classical oval. This is taken from what's a Dynamics Explorer satellite, and the images have a cadence of 12 minutes. So the Aurora isn't getting bigger, it's the satellite's getting closer to the Earth, okay? So it's in a non-circular orbit, but this limb is the day side, okay? So we've got a day side, and here's the Aurora. Anyway, we can see very clearly where the energy goes. Unfortunately today, we don't have a satellite with this capability. So we're back to ground-based all-sky cameras, and that's about it as far as trying to reconstruct this. And from the movies that you saw, this thing isn't a nice big homogeneous fat region of emission that's constant. It's highly structured, and words like substorm go with it. Okay, so this next plot, sunlight, okay, that's good. This is Rocketry, when people flew experiments through Aurora, specifically looking at the electron spectra, trying to figure out at what energy are the primary auroral electrons. And this is a whole bunch of different rockets. This is just an example from 1974. So our knowledge of this goes back a long way. But basically, there's a kind of peak. And in this peak is where the majority of the energy carried by the auroral electrons. There is always a tail of very energetic ones, but in terms of what we're talking about affecting at the SARE energy, it's this group here, okay? And if we, for whatever reason, pick A to be typical, okay? That was a joke. This is A. I'm going to pick the spectrum A and call it typical. Come on, guys. You're lagging behind me all of a sudden. Come on, let's keep after this, okay? Okay, so A is what I'm going to use, and if I integrate that up, now, the time is important because it's watts per meter cubed that we're talking about, but this is the local energy density, joules per meter cubed. So I need to have a time constant in here. So what I'm doing is I'm taking that spectrum, and what I need to do is assume how long is the aurora in one place. So this would be a very strong aurora, very bright in every possible way. It's also packing as much energy as an auroral form could pack. And 10 minutes, I'm assuming, is about as much as you can do. But it is effective. It's comparable. So for that 10 minutes, it's dumping into an atmosphere whose time constant is maybe tens of minutes to hours, if not slightly longer. So this would actually locally perturb, and that means the atmosphere above it gets heated, it's a bit more dynamic, and LEO satellites passing through this would notice the disturbance. But since this is localized in one place, and it's not global, it's not affecting our atmosphere significantly. Okay, so that was one. This is the Xray flares. You've heard a lot about Xray flares, but let's just make sure we're on the same page. This is the wavelength spectrum for our solar emission, if you like, going from 0.1 nanometer all the way up to, well, almost 6 10 to the power 6 nanometers. So 0.1 to 10 to the power 6. 1 to 10 is what I would call our soft X-rays. 10 to 100 is our EUV. So what's plotted on this, and it's an old paper. This is taken from Brasseur and Solomon in '84, but the picture was made at the Air Force Geophysics Lab a decade before that from rocket data. This part we know is very quiescent and is our solar constant. It's our white light that maintains our atmosphere in general. Lyman alpha is sitting here, and it does have a variability. But on here, what's really important is this region here is the soft X-ray to hard X-ray, the quiet sun and the active sun. Now, the active sun, I'm just referring to active regions in a more general sense, but not to a flare. The flare, and this would be a significant, it's a 3B on a scale that's no longer used, but the modern day X-class flare nomenclature, this would be a large X-class flare. And what you can see on this axis is the irradiance, which is the watts per meter squared per nanometer. Okay, it's done as a function of per nanometer. Changes by almost 3 orders of magnitude. And that's where our earlier understanding of the EUV is dominant and there's a small X-ray peak underneath. And I keep on wanting the SARE to be this lower one. And this is the reason. During this period, an event like this, the EUV changes by maybe a factor of 2, tens of percent. So the EUV can't keep up with what the flare energy looks like. And we end up, the 1 to 10 nanometer photons dominate what's going to happen. And if I do the calculation, again, I need to tell you how long the flare lasts. So what we've got is an X-class flare, a rather large one. It's dumping its energy now in the SARE. And I've assumed it's bright for 20 minutes, which I think is not that unreasonable. But with that, the flare is dumping this. Now, I should also tell you right away, where is the flare active? Well, it's back to our solar zenith angle. This is the kind of information if you've got the sun directly above you. As you go to higher latitudes or towards dawn or dusk, the intensity drops and the energies distribute over a much wider altitude range. But in this particular altitude range, it's putting energy in faster than the thermalization processes of the gas can handle it. So it most certainly is active. Okay, so this comes to our third one, which is our electrodynamic system, the MI coupling. The surface that's being drawn with the kind of yellow cycles, if you like, represent that two-cell electric field mapping down. These orangey lines try to indicate to you current sheets that are coming into the upper atmosphere along magnetic field lines. And of course, this surface that we're talking about is where the Aurora, or if it happened to be during summer and got an X-class flare, the ionization's gone up. If the ionization goes up, our conductivities, Hall and Patterson, go up, and therefore this enhanced electric field, its Joule heating, is gone up too, in about the same region. So all three of them are dumping energy under a summertime condition into literally the same altitude range. This is just a plot to show you for a particular calculation what the Hall and Patterson conductivities look like. So it will take a minute. This is our altitude scale again. Down here we have Hall conductivity during the daytime, and then slightly higher is the Patterson. And the dotted lines over here are the nighttime Hall and Patterson, which haven't gone away. But again, as I said in an earlier figure, it's not an auroral nighttime. Here's the daytime. Okay, so if I then do the same analysis, the Joule heating, if it can be maintained, is significant. So what we've got is, I've placed it here for 3 hours, so I'm saying that the main phase of a big storm might last 3 hours. And this electric field, so there's a whole bunch of assumptions here. The auroral conductivities must be underneath where the electrons are going, or else you don't get this large conductivity. If the conductivities aren't large enough, the Joule heating rates are reduced significantly. But everything goes well. Our major storms over eons can actually impact the local thermal balance. And of course, that's, to be honest, not a surprise to us. Present-day space weather does disrupt geospace climatology on short time scales of hours to days associated with specific space weather events. What we have is, once the storm occurs, the recovery of the LEO environment that the satellites are in takes about 3 days. So that disruption, density increases, temperature increases, takes days to kind of moderate itself. So we're very familiar with that phenomena. The GPS geolocation tools are similarly disrupted. Now, there is a thing called the Wide Area Augmentation System. How many of you have heard of this? Okay, Nick has heard of it. You may leave now, Nick. Anyway, this thing was set up by the FAA, and it was primarily for the United States. Way back 20 years ago, not quite 20, there was a realization that during geomagnetic disturbances, the normal GPS systems were kind of not accurate enough, that they were kind of, they're not failing in that sense, but the accuracy with which they can give you your position started to drift beyond 50 meters, which was an FAA kind of requirement. So what they did was they installed across the United States, so it began in the United States. The idea was to have many 20 to 30 very high quality GPS ground receivers, so you could on the fly in real time create a better ionospheric description based on that. That information was immediately in what's called the WASP receiver, the GPS receiver on the airplanes. It was bounced off satellites, so every airplane with a WASP receiver got this much improved information. But even that, in the early days, didn't work completely. Even then, airplanes got kind of warnings, and the warning was simply, if the WASP GPS system couldn't give you an accuracy of 50 meters plus or minus 50 in its location, it just shut down and didn't tell you anything more. Which, of course, if you're flying airplanes with this better knowledge, and the main thing they were doing with it initially was our airspace above the United States has lots of airplanes all the time, and the kind of window or the tunnel you were given was a particular size. But there was still too much air traffic. So the FAA needed some way of reducing that by a factor of 2. And the WASP system was designed to do that. So all of a sudden, your kind of tunnel, if you like to call it that, between two airports was uncertain because your WASP system went offline. Now it's been much improved, and they can do many more, even better things with the improved systems. But this idea that a geomagnetic storm or space weather can disrupt geospace such that things like airplane travel can be affected. And we haven't even talked about landing with GPS. How many of you think we're going to do that soon? How many of you have been in a car that's a GPS car with no driver? No one? How many of you want to? No one. Okay. See, so this is the benefit of geospace and severe space weather. But humans get pleasure of seeing geospace's beautiful aurora. Okay, so the aurora, when it gets down to mid-latitudes, Boulder, Logan, our cities, every now and again get these phenomenal auroral displays. So has anybody now agreed that they're going to go and find the aurora? I haven't convinced you yet that you're going to go and find it. Come on. Thank you, Nick. Okay, let's continue. Okay, is there evidence that space weather is affecting exoplanets? Okay, so this is the part that's kind of newer as far as I'm concerned. Okay, so stars and atmospheres, the solar stellar system, independent of space weather. So in order to do any of this analysis, you've got to start with something. And like we do with the Earth, you start off with an atmosphere around a planet. So we actually don't know much, but there is, if you scroll through NASA websites, you can find something like this. which isn't exactly a Hubble picture. It comes from just images from NASA. So I have no statement of validity of what we're looking at exactly, all right? But there's Jupiter on here, and there's the sun that's been placed on top of what is a NASA reconstruction. It's a Hubble measurement of an atmospheric structure around an extrasolar planet, HD 209458b. I apologize, I'm not an astronomer. I have no idea how to interpret this. But this object, what's important about it is that there is some initial information about its environment. And if we can get information like this on kind of exoplanets, then the analysis we've been talking about today can be done for X-ray fluxes, okay? Once we know that. So in this case, they talk about there's a lower atmosphere at 1,200 Kelvin with possible clouds. Now that's not way outside our lower atmosphere, although our lower atmosphere is maybe 30 degrees Celsius, which is about 300 Kelvin. So it's not clear quite what they mean by lower atmosphere. Most certainly they have a middle atmosphere, and they've indicated sodium is present. Now, is that meteoric debris or other things? And then there's a transition zone at 5,500 Kelvin. And the transition zone at that kind of temperature, from what we've said already, 5,000 is a kind of magic number for hydrogen, neutral hydrogen genes escape. So now we have another structure that they identify as a much hotter structure, which you'd expect, with carbon and oxygen measured. So they have some information about the dimensions. They have information about temperatures and planetary maybe composition, but quite rudimentary. But given this is a starting place, what we've been talking about, some of what we've done with the photons, we're going to be able to do very readily with these kind of planets. But this is a starting place. Okay, so the first of 3 space weather impacts. So let's begin with the X-ray flares this time. The neat thing about this is the X-ray instruments, the astronomers' instruments, on rockets and satellites have a huge database and knowledge of stellar X-ray luminosities. Now, you've heard about this week already, but it's just phenomenal that they have a whole sequence of huge satellites to measure that which we can't measure from our own sun. Our solar people cannot measure this 1 to 10 nanometer band with spectral resolution such that we can accurately put solar flares into our atmospheric, ionospheric models. The trouble, of course, is what would happen if we turned one of these instruments towards our sun? Yeah, it's going to fry instantly. So we've not even got the luxury of trying to take an old satellite and just turn it gently, just have a little peek. No. Anyway, here's the plot that I'm sure you've seen. Have you seen this one during the week? Okay, so it'll take a second to talk it through. This is a timescale log age, and the important 2 circles are our sun. And it's basically X-ray luminosity. So that means they've integrated the X-ray spectrum from some value to some other value. And I don't know the 2 limits. It may be instrumental as to what they all covered. But the other axis is this log luminosity, X-ray luminosity. And they've done it for 4 different kind of classes of stars. What class of star is our sun? G. Okay, so there's some G, some additional G's, and here G. So the first thing is all of these others are younger than our sun. Okay. So this is an ionospheric physicist interpreting for you X-ray astronomy stuff. But assuming I'm not too far off the truth, we'll continue. The neat thing is the way they did the ages. They looked at clusters. So the Hyades, the Pleiades, where there's an expectation that the age is somewhat self-similar. And that's why it's banded like this, the different targets. But each one of these points isn't a single observation. It's observation of over like 100 stars in that classification. So the data set is very rich, and it's not spread all over the map, but it's all identified here as being significantly larger than the sun. So what can we say about the sun? So the first thing is the lower point is our quiescent sun, the soft X-rays. And you can draw however you want to draw the lines. But there's 3 orders of magnitude there. If we take our X-ray class flare, it's up here. Now, you might argue with me. I pointed out the next class flare, its peak was 3 orders of magnitude larger irradiance than that at a quiet sun. But this is only 1 order of magnitude difference. And the difference here is that this is an integral over a spectrum that has a very high spectral sensitivity. So that the integral, although it's only 10 times, at the peak it's going to be at least 3 orders of magnitude larger. And the peak is the part, it just turns out, for our sun and our ionosphere, it's in the peak that most of the energy is, and it's ionizing in what we call the SARE. Okay. Okay, so okay, let's just repeat. Okay, so here is now, in terms of energy deposition, our ionosphere for the quiet sun, the EUV and the X-rays, and we've seen this before, are 2 kind of peaks. Okay, the EUV is the upper one, and the lower one is the X-ray. So of course this next panel, it's not up there yet, is what happens a big X-ray flare. Okay, and the big X-ray flare, you can see right away, the EUV flare is still here, but this Oxys is kind of a linear scale, and it's kind of just buried in here, but it's still present. And okay, good. So now what we've got is our other formal introduction to the star-atmosphere interaction region that I'm going to call the SARE. So these observations of X-ray active stars, the kind of quiescent levels are way higher than ours, and they have things called super flares that have been mentioned. We're not even talking about the super flares. We're just talking about normal X-rays. And remember, it's to do with an optical depth. So although you go 3 orders of magnitude higher in the number of photons coming, as long as they all have the same energy, they're going to end up being absorbed at the same place. So this SARE isn't going to go up and down based on there's more photons coming. As long as the photon energy is the same, it's going to bury that energy in the same place. Now, clearly, if the amount of energy deposit is continuous and very large, then as long as you know the planet's rotation speed, you can figure out how long it's going to be a hot spot on the SARE, and therefore what kind of loss of atoms is going to occur based on the heat that's being delivered. So now we've got the SARE on every kind of exoplanet, and the stars that we've been looking at would have fluxes that are going to elevate this, if it were the Earth, way up here. Now clearly we don't have a lot of knowledge of exoplanetary atmospheres, so we can't really push this analogy. But we do know that such a region would exist, and what it will do is simply generate underneath it a kind of protective layer. The energy flow through this is going to be negligible. Basically, the atmosphere and everything else underneath stays the same for this particular mechanism. I would fear there's some hard radiation that's going to do more damage down below. But above is where it's going to get interesting. The SARE atmosphere and the ionosphere are heated, and the heating would lead to enhanced atmospheric loss rates, reaching levels of Jeans escape. The 3,000 Kelvin that we had for a possible grand maximum for our Sun-Earth system doesn't really change our dynamics much. But these kind of levels of X-ray luminosity that we've been looking at on the Earth would push this and our models aren't capable of this much energy deposition in such a short time. So we don't know how hot the gas up here would get, but getting up to 5,000, maybe 8,000 would be very doable, in which case there's huge outflow of our neutral atmosphere. And of course, as this gets depleted, there has to be more neutral gas put in, or the SARE just drops a little bit with time. Now, the density keeps on increasing, so it's not a very linear drop down. As you get denser and denser neutrals, the SARE takes longer and longer to drop down. But that would be the mechanism by which space weather, through flares, would remove an atmosphere. Okay, so this is just putting it together. Our 3 orders plus would be somewhat a timid thing. A very hot, dense E-region will form. The atmosphere above will be extremely hot and potentially in a Jeans escape condition. Satellites will now be in a challenging hot environment. Now this, from a technology point of view, is perhaps more interesting. You've now got the neutral gas that you're kind of flying through, well, unless you've gone really, really high. But you can't get away from the fact that everything is much, much hotter. And the interaction with your satellite surfaces, especially if there's a significant amount of hot atomic oxygen, is going to be really a hostile environment, to put it mildly. Issues like radio communication and other things are all up for grabs in a negative way. So now, how a magnetosphere would then introduce more complexity. But this one we can't do too much with. The magnetosphere can be viewed as a giant energy collector and focused concentrates stellar CME, stellar wind energy into intense beams that impact the upper atmosphere. Well, we've gone through this and showed how that works. But we have no data from our exoplanets or stars on solar activity other than through the flares. And of course, the flares, one could very positively argue the CMEs must be gloriously huge and continuous, or one can go the other direction. So it's clear that we need measurements here in order to see whether or not stars at these younger ages, which are more active, actually also ramp up the size, the energy content, the speeds of these structures. And the aurora precipitation and Joule heating, well, the processes most certainly exist, but we've got no data yet from an exoplanet point of view. Yeah. We've got NASA. NASA can create these things. So, we've got a nice picture, although I can't add much to it. This idea that the magnetosphere most certainly provides some kind of boundary, and observationally there must be measurements that can be made that indicate a magnetosphere exists. And you've heard this last week more than one attempt to tell you how we're going to proceed to make measurements. But as far as we're concerned, at this time we have no evidence that another planet outside our solar system has a magnetic field. The issue of the magnetic field is not just its strength, but its orientation. Is it a dipole? And we'll maybe touch on that a little bit later if I don't run out of complete time. The idea really is that once we know something about the magnetic field, there's a lot we can now do. But at this point in time, this is our speculation. Okay, so the speculation will quit there as far as the exoplanet world. Now we come back to our original topic, was the past and the future of our Sun-Earth system. And we can actually do some things that there is evidence for. Billions of years ago. So we do actually know that at these earlier times, there was an abundant amount of CO2 in the atmosphere. Okay, so so that meant our atmospheric composition changes. And studies have been done. The one thing we talked about earlier is, if that's true, then the greenhouse gas in the lower atmosphere is one of the problems for us humans. But in the upper atmosphere, it's a radiator. It dumps energy in the form of IR radiation out into space, so that the thermosphere, it's actually going to cool it, okay? So hence the CO2 is competing against the enhanced EUV fluxes to cool the thermosphere. There are models going back well, the models don't go back billions of years, but they predict. Didn't even predict. They try to explain to us what the EUV fluxes might have been like. And it is probable that they were larger than they are today, depending on our models. And for Venus and Mars, we already know it's rich in CO2 in the thermosphere. So this plot gives you an indication of how the CO2 affects the kind of studies we've been doing. On this axis is the exospheric temperature. Now, our comfort zone is somewhere in here, maybe at 2,000, 2,500. This axis is the XUV flux. Now, for solar minimum, we know we're sitting in here 2 or 3. And for solar max, under our present conditions, we're over here. So these are our two lines. The scale that they've chosen to describe here, CO2 equals 1, is our present day level. Okay? And what we're kind of looking at is the kind of combination of, if you know how much EUV is coming, based on this kind of amount of CO2, the cooling only works so far, and the effect of the cooling means that by the time we get 4 or 5 times the, 4 or 5 units of the XU flux that we've got today, we're going to end up losing hydrogen. The temperatures have increased sufficient. So although we're talking about a CO2 like we have today, with the older models of the atmosphere, we're still going to run into this problem of reaching this point where our temperature is up by about 5,000 Kelvin and the hydrogen is blown off. For our kind of other planets where we know there's a lot of CO2 today, these other lines are relevant, and it would take a lot more solar EUV before we start losing. Now, this kind of opens up questions like, well, what was the rest of the atmosphere doing? What were the kind of different species? So each one of these studies should be taken with a pinch of salt, to say the least. We're kind of conjuring up atmospheres. We're recycling atmospheres. This atmosphere gets recycled. By the time you get our normal EUVs, as we think of them, we would be losing the atmosphere. So there are scenarios from the past, and this was a billion years ago. This is, I guess, in a very similar kind of way of looking at that past history. This is kind of us at the Earth today. And here's our exospheric temperature that we're kind of experiencing. The kind of modeling of prior atmospheres, figuring out what the thermospheres looked like. If you go back to a billion years ago, here's this magic 5,000, just a tad over 5,000 in this diagram, where we suddenly, the hydrogen gets blown away. One has to get up to about 10,000 before our oxygen would blow away. But back then we've got CO2, but as you saw on the atmospheres of Mars and Venus, there's lots of CO2, but there's lots of oxygen as well. The photochemistry generates these other species, so that somewhere back here, not that much further back, we would be losing kind of other atoms that we're perhaps more friendly to. Okay, here's another piece of our past history that tells us something. How many of you have heard of the dipole field flipping? Okay, so that it's kind of normal everyday conversation in the sense that I know USA Today doesn't talk about it very often, but there has been recent talk about, are we getting near a reversal? And if it reverses, what actually reverses, or how does it reverse? And of course, that's a kind of real hard question. The one piece of data that is kind of collected, well, how do they get this information? Where is the information from millions and billions of years ago that tell you the orientation of the Earth's magnetic field? In the ground. Where about in the ground? In the oceans and places. Where does it get imposed on? Lava. Yeah, you need a material which is able to align its little dipoles, if you like, in a particular direction before it cools and hardens. So anyway, given that background, whereabout is this process going on very well just now? Hawaii. I mean, it's pouring out liquid stuff that goes hard, reasonably quickly. Yeah. So anyway, that's kind of our geologists have come up with this. At the present time, they struggle. It's pretty much the dipole moment, the virtual axial dipole moment. But the higher moments may be particularly important. And the reason that is because the process of the reversal is not clear. Does the dipole just have different orientations over a certain length of time until it's round? Or does it one day just go the other way? But the other arguments are the higher order moments take over as the dipole itself kind of diminishes and the system recovers in the opposite direction. So anyway, there is information that we've got on that part of our history. This is out of one of these textbooks. Millions of years today going backwards. And the alternative black, white represent times in which the orientation was one way and then the other way. So this is, of course, our present day, and we have these. So there is this one here where there is a data set indicating that there was a kind of double reversal over a period of only 10,000 years. Now, this data is still to be interpreted. More information is needed and things like that. But this is kind of one example of where we are. Another example is kind of something like this. One can actually attempt to kind of look at the transition process itself. So this is the post-reversal, and this is the pre-reversal state as it rapidly drops to this point. So this amps per meter squared, 10 to 22, 1 times 10 to 22, appears kind of magical in the sense that if we get there, we're going to be in a flipped state. Okay? It turns out today we're at this number 8. And you could say we're on this slope. And this slope is moving fast. But we're going to be dead before it goes. Yeah, don't worry. So in the other sense, the recovery back to this large number that we currently experience is a relatively slow process based on information as we see it. Now, the 10,000 years is a problem because on this kind of curve, the 10,000 years is a rather small time period. Okay, so what we do know is that the largest values of this Earth dipole moment, if you like, is about 10 times 22 amps per meter squared. And the flip value, as I said, is 1. And we're currently at 8. And the question, can it just suddenly drop down? This is kind of, it's speculation more than geological theory or dipole theory. I guess did the dipole theorists talk about the Earth's dipole? Okay, so this then is just an ionospheric person's kind of thinking about. The reason you might worry about where the dipole is pointed is things like, where's the Aurora? Okay, the Aurora forms in regions connected to the magnetosphere, but if your poles, or a magnetic dipole is sitting in the equatorial plane, you can do some neat geometry to try to think of what the magnetosphere looks like and where the Aurora would be. But there is some interesting relevance. Okay, Friday's magnetospheric lab. So that was an attempt to work us in that direction. Okay, and this is kind of our state as we go over the kilo years. Here's today, when you go back, and this is pretty good data, if you like, with what you might call a spread. I'm not sure it's a standard deviation, but it does indicate a slow kind of rise. And this is why some people kind of are speculating this thing is turning over rather rapidly. You all know that the Earth's dipole pole and the actual shape of the field itself isn't very pure dipolar. And on any given year, you can actually see the point at which the dipole the magnetic field is vertical to the surface, or where the dip, that's a dip angle, or its magnetic field strength is its maximum, that polar region is continually moving. In the southern hemisphere, it's even less dipolar, and the separation between the magnetic strength pole versus the dip pole is quite large. So we're in a non-dipolar world at best. Very few of our models incorporate that. That's it. Thank you. Yes, ma'am.
So it's thinking about this offset of the magnetic field, where we have an asymmetry in Earth's magnetic field. We're also seeing an asymmetry currently in the sun's magnetic field, and it seems to be associated with the extended minimum conditions.
Oh.
Does that have something potentially to do with the fact that we have had such a long split with time of polarity everywhere? Is that speculation?
Yeah, sorry. You've pushed me over the edge, as much as I like to answer questions. But we've got Amitava and Dana here. Okay, so there was a statement about this long solar minimum that we've got, and the sun's magnetic topology, if you like, not being quite as aligned as you'd think it should be.
The non-symmetric hemispheric magnetic field. Okay, so one is lagging behind the other in terms of symmetry. So
one thing to remember when I talk about it, it's all about those multiple moments. Right. So when you say dipole, you're just basically taking in the idea of anything occur. If you say an offset dipole, you're taking some of the quadrupole occur. Anyway, but the sun had this weird situation this past cycle where sort of, if you wanted to just look at the sign of one rotational pole changed sign before the other one.
Well, so my question.
Mm-hmm.
Right. Well, my question is, so there's speculation that off-symmetry between the two hemispheres plays a part in why we have such an extended minimum. Right. So if the Earth's dipolar field is anti-symmetric at the moment, does that go into explaining why we have such a long period of a particular polarity?
Hmm.
Other people will tell you the reason we have an extended cycle really has to do with deeper effects. You can actually see a signature where the oscillation through the cycle. The meridianal circulation is what you're hearing about. And that appears to have slowed down. So we actually saw that cycle 24, the last cycle, approaching for a longer period of time. Don't think cycle 25 is on such a slow track.
Other questions?
Just to make one comment, just to follow up, is that you look at class minus simulation of Electrodynamic. They're not done for completely realistic parameters. But given that, one of the simulations working on, it has seen flips to Electrodynamic. And the question is, can you extrapolate all of that has been done, of course, in finite time, where the Earth is thousands of years, like that. So there's a question of whether you can extrapolate the result. And it all gets done at a certain level, or these transport parameters that are there in this code. They're not measured very precisely, as you know. You can make guesses about them. So there's a bit of a game involved in what is stored in the parameters that the advanced simulations code. I know equally well that it's going to be a strong reactor. Nonetheless, the physics of this reversal is to allow them to extrapolate is what we discussed and what the record said.
Just a question about the words. So when you see like pictures of boards, they can seem kind of small, like when you're on the ground. But like they're big, but they're not like
Mm-hmm.
like the pictures can sound like
So,
smaller, and like when you're on the ground, it looks like they're only like, in your field of view is not that large.
so
Geometrical.
yeah, no, it's kind of a lesson for you guys to learn. If a modeler says they've got Aurora in their model, what you're just describing is what's actually going wrong. We integrate up, or we take averages over a kind of particular area, and in most of our models, the kind of area that we'd have in 1 pixel, if you like, that we call Aurora, could be 5 degrees by 5 degrees, which is 500 kilometers by 500. And as you say, the structure, even extent, it's very hard to ever see an aurora that's uniform over these scales. Some of us are down to 1 degree by 1 degree, which might be 100 kilometers by 100. And then you ask, well, how are you getting that auroral energy in there? Where does the auroral electrons come from? Well, the bats or us is a nice example of people trying very hard to get realistic aurora, real energization mechanisms. But to be honest with you, even in these models, the conductivity layer isn't necessarily responding to what you're sending down as aurora electrons. So the kind of observation you're making happens to us modelers in many fields. The idea that the scale size that's the dominant scale size is actually the one we're using because of computational resources, making the problem doable. So that's a very neat shortcoming, if you like. You can see it in the real world as not being representative of the aurora, and we all have auroral ovals. There's a thing called the Hardy auroral oval that many modelers use. It's empirical. It's basically 6 levels of geomagnetic activity, and it's taken the DMSB satellites data from like 15 years and kind of munged them as best they can into these averages of 6 conditions. So what you get are boundaries, you get peaks, but it's all homogeneous. Homogeneous is not right, but it's continuous. It's not as non-continuous as you saw. It's way better to see the real aurora than to look at a model. It's honest. And one more pitch, The only pitch I'm after is for you guys to see the aurora while you're young enough to appreciate it. It's a good observation. But it's a kind of lesson. If you use someone's model, try hard to find out what the limitations, what are the assumptions. And the real problem with that is if you've got 20, 30 years of development, when you read the most recent paper, that paper won't tell you what these assumptions were. You've got to go back 20 years to find out where they made the assumptions and what they were. It's better to find the individual, buy him a beer, and say, hey, come on, tell me, what did you really do? Yeah? Okay? So your next assignment, I believe, if Nick's around still, is to actually look at ionospheres from a computational model and determine key characteristics that we've talked about. Should we release them?
Thank you, John. Good as always. I was disappointed, though, you didn't hand out any envelopes. I vow to do that sometime in my class, but I didn't do
Okay.
it. You can de-mic yourself, too.
Okay.
So
Uh-huh.
in the talk in the morning, you mentioned 2 chat studies.
Yes?
So do you have the wordings for that?
Oh, sorry, let me shut this down.
Right, and I agree with what you're doing, that's great. The aiming, of course, is magnetic observations, and of course that is global either. So there are, well, that's ground truth. That's the problem. Yeah, it's not ground truth. And every which way you look, we don't have as many points of measurements resolutions as we would like. It's hard to do. I mean, in the place where there's a good continuous set of measurements, you should get a check mark and say it's really good. And then somewhere else will run. It's interpolation. So how do you say the whole model sucks? What they should